Pleasure to be here. I had to walk all of 6 blocks to come here.
Thank you for the effort.
Yeah, I love giving talks when I don't have to fly to give the talks. Well, thanks for coming so numerous. I apologize for those of you who have to stand in the back. If you prefer to sit on the floor, there's probably a lot of space here. I'm not sure if you can like short circuit to this room, but yeah, it might be a little difficult to get here. Anyway, I hope I'll make it worthwhile for you to stand for 40 minutes or more. So we have this sort of highly technical process here for projecting that consists in me showing my screen through Google Hangout with this laptop that then goes to the screen. So I hope this is going to work. So I'm going to talk about deep learning and AI, and this is going to be a bit of an overview of a lot of applications and things that we do with deep learning. And I can dig into details for any aspect of this, which I won't in this first presentation, but during the question session, perhaps. So you all know what machine learning is all about and supervised learning. So the reason I'm showing this to you is that the vast majority of success of deep learning so far in applications such as image recognition, natural language processing, etc., is supervised learning. But there is a bit of applications also of unsupervised learning, and I'll talk about this a little bit, mostly for natural language understanding and representation. But most of the applications are supervised, right? So the model is something you know very well. You show a bunch of examples. You compare the output with the output you want, and you adjust all the knobs in the system so that you get the answer you want. And you keep doing this with millions of examples until the knobs stop adjusting, just stochastic gradient descent algorithm. And really what's new about deep learning in this context is the idea that instead of the usual process that I'm sure all of you are familiar with, where you have a data set, you spend a lot of time preparing your data set, and then you spend a lot of time designing features so that you can plug this data set in your favorite classifier, predictor, whatever you want. That's a manual process that a lot of you, I'm sure, have been spending a lot of time doing. And the main idea of deep learning is that you replace this by an automated process that just learns the feature extractor as part of the whole process. So instead of having a separate feature extractor that's engineered on which you stick your favorite classifier, logistic regression, trees, SVM, whatever you want. You build this machine as kind of a cascade, if you want, of blocks, all of which are trainable. And we're going to train this entire thing end to end. So, of course, because those models are more complicated, they have more parameters, they require more data to be trained properly, generally, than those. But we have data now, or at least at Facebook we have data. I'm sure wherever you work, you have data as well. So one of the first systems. This is a little choppy, but I guess you get the idea. A lot of applications, like very heavy applications of deep learning these days, are for image recognition, video, labeling, speech recognition. And almost all of them use a model called convolutional nets, which is a model that I contributed to develop back at Bell Labs when I was working at Bell Labs across the river, kind of south of here, about 25 years ago or so. And this is kind of a very old convolutional net from the early 90s that we, at the time, trained to recognize handwriting or handwritten digits. And so what you can see here is the succession of layers. And so each, for those of you, I'm sure many of you are familiar with the basic idea of deep learning. Maybe a few of you aren't. So how many people here know what backprop is, backpropagation? Okay, about half, I would say, of the people. Okay, so this is a particular type of neural network. And so neural networks come in multiple layers, as I showed earlier. So each of those columns here is a layer. And each pixel represents the activation of a particular node. And you can think of each node as being very much like a single unit in a logistic regression, right? So it computes a weighted sum of its inputs and passes the result through a sigmoid function. And what you see here is the value of the output value of the sigmoid. So white is -1 and black is +1 or something like that, and then gray is something in between. And so what we do, of course, is when we train this machine is that we learn the weights of each of those nodes. using gradient descent, and that's done with the so-called backpropagation algorithm. So the basic idea is you take an image, you run through, you compare the output that you get with, from the neural net with the output that you want, and then using a kind of backpropagation algorithm, which I'm not going to go into, you compute the partial derivatives of this loss function that measures this discrepancy between the output you want and the one you get with respect to every single coefficient, computing, they're entered into the weighted sum of every single node. Okay, so this is back in the old days, the computers we had were not nearly as powerful as they are now, of course, and the networks we could run were relatively small. So this is a relatively small one. And it's called a convolutional net because we build this architecture in a particular way, in such a way that every node is connected to a local patch on the input. So this is kind of represented here. So one particular node on the one of the output planes is only sees a small patch on the input and computes the dot product of this patch with a set of weights. Those are the learned weights, if you want. Okay, so you get the dot product of those two things. You put that here, pass that through a sigmoid, and that's how you get this this value. And then you repeat this. You kind of slide this mask all over the image, and for every location you get a resulting output. So this is like a the filter operation in Photoshop or whatever. That's exactly what this does, except the weights here are learned as part of the learning process. Okay, so you can think of each of those nodes as being sort of an elementary unit that does logistic regression, but it learns a feature. It doesn't learn the output. It learns kind of an intermediate representation of the input that will be useful for the classification. So that's one type of layer in a convolutional net. And the second type of layer is what we call pooling. So we take one of those maps. Each of those guys is called a feature map. The result of applying a convolutional filter to the input plus a sigmoid. And then we take each of those maps, and we basically reduce the resolution by half. Okay, so take that, shrink it by half, you get that. It's not exactly a shrink in this particular case here. It's we compute an average, and we pass that also through a sigmoid with a gain and everything. But the more modern versions of this use max pooling. So you take 4 values, compute the max, and then that's the value you put here. You do this separately for each of those maps, and then you repeat the process. So this guy now is the input to the next stage. Each of these guys are going to apply convolutional filters to each of those maps, add up the result, and that's what you get here. And the purpose of this is to combine features that are detected by the first layer in such a way you can detect combinations of features. So if this guy, if some of these guys detect oriented edges, these guys can detect combinations of edges like corners and things like that. And again, pooling and again, convolutions, etc. You can stack them up. The modern versions of this have anywhere from 20 layers to sometimes the latest version actually that won a competition very recently has 152 layers. It's become pretty insane actually. So that's a convolutional net, and it's trained with gradient descent essentially. This is actually a younger version of myself at Bell Labs, back in Homedale, New Jersey. This is my phone number at Bell Labs, no longer operating, and I hit a key, and it grabs the image. There's a video camera looking at it. It runs on the 386 PC, if some of you remember what that was. But in fact, the processors at the time weren't actually fast enough to run this at that speed. So we had custom code written on a digital signal processing board that was capable of the amazing speed of 20 megaflops. So that's early 90s, and eventually this kind of stuff made its way into systems that were able to read checks. My colleagues and I at Bell Labs in the early 90s and mid 90s built a system that was able to read entire amounts and locate amounts on checks and read checks, and that was deployed. And at some point in the late 90s, this was reading between 10 and 20% of all the checks in the US. So that was a big success of neural net, probably one of the biggest success of neural nets in the sort of first wave of neural nets in the late 80s, early 90s. And one of the cool things that we could do with this that had a huge impact 20 years later is that we realized we could use those systems not just to recognize individual objects, but multiple objects. So what we have here is a particular kind of convolutional net that instead of having a single output that kind of recognizes the entire input. You can think of this as kind of multiple convolutional nets that are whose input window is shifted on the input, and so each shifted version of this convolutional net, if you want, has a particular input window and produces a score for all the categories, and it's able to tell apart the 3 from the 5 even when they overlap, and so we can sort of pull out the best interpretation of this here with a very simple finite state machine. So the ability to recognize multiple objects, separate a figure from the ground is really important, because that's basically the property that allowed us to use convolutional nets for essentially recognizing objects in natural images. That's kind of a fun one here, where the thing morphs from 6 to 5 to 3 to 7, etc. So in particular, we could do things like this, like train one of those convolutional nets basically as a binary classifier. You show it images of faces and images without a face, and then you train it to turn on when it's a face, turn off when it's not a face, and then you swipe that network over an entire image at multiple scales, and it's going to light up whenever there's a face in its viewing window. In fact, this version was slightly more sophisticated. It was able to even figure out the pose of the face. This was done in the early 2000s when I was working at NEC for NEC labs in Princeton for a short time. This is actually my grandparents' wedding.
Wow.
And a couple of years later, some of you might recognize Washington Square Park here. Sorry for the choppiness of the video. That's the Google Hangout connection. We trained a convolutional net to, again, as a detector, to showing it images with a person and images without a person, with a pedestrian, without a pedestrian. And with enough training samples, it's able to basically pick out pedestrians wherever they are. And there were several methods to do this at the time that were kind of more conventional, not entirely based on just feeding raw pixels and running through a convnet. But eventually this kind of won out. So there's a lot of, now that we have tons of data, this kind of method really beats everything else out there. And a few companies now are building systems for self-driving cars and safety systems for cars that basically use this to detect obstacles like pedestrians. So back in the mid-2000s, it was pretty clear to us that we could use this kind of technique for robotics applications. And DARPA was kind of foresight to fund a project on the use of machine learning in robotics, in mobile robotics. And so this was a program called LAGR, which means Learning Applied to Ground Robots. And here's the robot. It's about this tall, weighs about 100 kilos. It's got 3 sort of laptop, 2005-ish laptop type single board computers in it, and so not very powerful. And of course, you can drive robots like this using stereo vision. So you can, use the cameras, figure out, by triangulation, how far something in front of you is, whether it sticks out of the ground or not, and then, decide whether it's traversable or not. So this is what stereo vision tells you. But stereo vision doesn't work at, more than about 10 meters. Beyond 10 meters, it's very difficult to estimate whether something sticks out of the ground or not. So that's where we use convolutional nets to basically train the system to label every pixel in the image as to whether it's traversable or not. And I'm actually going to show you a video of this, if I may. Hopefully that won't be too choppy. It's a little choppy. So, right. So this is what we show to the network. It's bands that are extracted from the image, and we send to the convolutional net. And we train it to produce labels. So this is the kind of output it produces. That's coming out of stereo, and that's coming out of the neural net. So the network labels every pixel as to whether it thinks the robot can drive on it or not. And it's trained with data that's been collected by just running the robot around and figuring out if something is an obstacle or not using stereo. So that, after you figure out, if something is traversable or not, you can put the traversability index in a map and then use the map to navigate around. So here we basically shut down the long-range vision system of the robot. We just basically cripple its vision. It's completely myopic. You can only see 2 meters in front. And the purpose of this is to test the control system. So here, my former student Pierre Semanet, who's now at Google, jumped in front of the robot. Here, the robot has full vision, but they're trying to be really annoying. The other person here, Raya Hetzel, actually leads the robotics research group at DeepMind in London. So this was done in collaboration with a small company in New Jersey called Netscale Technologies, which was recently bought by NVIDIA, and those people work on the kind of self-driving car technology for NVIDIA now in New Jersey. If you want to work on self-driving cars, you can work for them in New Jersey. Okay. So this problem is called semantic segmentation, and to some extent, that's kind of the ultimate problem in computer vision. Can we label every pixel in an image with a category of the object that that pixel belongs to? So something like this. And in around 2010, 11, we started having really good results with this. Oh, the video here is really choppy. So this is down in the NYU campus, where we have someone wear a helmet with USB camera, so we can have panoramic video stitching, and then we run this through this network, and it tells us that's the road, and that's a building, and that's a window, and that's a car, and etc. Yeah, it actually ran at, we had a hardware implementation on FPGA that ran at about 20 frames per second. But on GPU, it runs real time as well. I mean, modern GPUs, it runs real time. So it makes stupid mistakes, like it says desert right here. This is Washington Square Park. There is no sand that I'm aware of. Or at least no beach. But it's as good as it got. I mean, this thing was the best system of its kind at the time, beating the other ones in terms of accuracy by quite a big margin, but also in terms of speed by something like a factor of 100, even running on a regular CPU. But at the time, the computer vision community was extremely skeptical that this was going anywhere. And so they were dismissing those results kind of flukes, essentially. Until something happened in 2011 and 12. So a bunch of people at Stanford and University of North Carolina, Fefeli and Alex Berg and other people collected this ImageNet dataset, which had 1.2 million training samples of objects, images from the web coming from 1,000 categories. And at the same time, it started to become practical to buy those high-power GPUs, programmable with CUDA, and they cost, $1,000 or so. So you could buy a bunch of them and put them in a machine. And the first people to implement convolutional net efficiently on GPUs were our friends at University of Toronto, Alex Krzyzewski, Ilya Suskever, and their professor Jeff Hinton, who is an old friend of mine. And they basically totally destroyed the competition with this. So they had a very large convolutional net, and they called this supervision. And at the time, all the competitors were getting something like 26% error on this data set. And they got 15%. And all of a sudden, the entire vision community said, okay, this is like, we're never going to catch up. So everybody stopped everything they were doing and switched to using convolutional net within months. It was amazing. I've never seen this anywhere else. This kind of rush to kind of completely changing. It was clearly a revolution. The same thing happened in speech recognition about a year or two before that, where groups at Microsoft, IBM, and Google, almost all at the same time, perhaps Microsoft a little earlier, started using neural nets as the so-called acoustic modeling part of speech recognizers, and their error rates went down by a factor of 2. And so again, all of a sudden, the entire speech recognition community, which basically had been sort of very kind of conservative for the last 15 years, not really changing the methods, all of a sudden completely switched to using neural nets for acoustic modeling. And so the next year, in 2013, pretty much everyone started using deep learning and convolutional nets, and the error rates went down by quite a bit. This was actually a student of my colleague Rob Fergus, Matt Zieler, who got the best results here, but he was using kind of extra data. Before he graduated, he had another system that actually placed third. We had another system in NYU that was tuned for doing sort of localization more than recognition, but did pretty well in recognition as well. And then by 2014, again, the error rate went down. Google kind of really ramped up their effort there, and now I think the error rate on this data set is around 3.5% or so, which is above human accuracy. So this data set has 1,000 categories. Some of those things are obscure breeds of dogs that most of us have no idea what they are, and so a trained, sort of a decent human kind of training himself or herself to recognize the thing will get about 4 or 5% error, and those systems are better, also faster. So this is the learning algorithm running. So these are the weights, those little filters that we use for the convolution, the first layer in one of those convolutional nets. As the system learns, they kind of start from random configurations, and then more or less as time passes by, they start acquiring structure and turn into oriented filters. And when you talk to neuroscientists, they tell you that the kind of function that neurons in the primary visual cortex area are doing are very similar to what we see here in terms of the what they call the receptive fields. So one of the things we're able to do in the 2013 competition was to train a system to not just recognize but also localize and detect and localize objects. It works really well for burritos for some reason, and various objects of various kinds, and discriminate white dogs from sheeps and different types of white dogs, and etc. So that worked pretty well. But in the meantime, in the last 2 or 3 years, there's been a lot of progress in this. So this is a system that was put together by a bunch of people at Facebook AI Research who work in my group. But I was not involved in this work. I'm not a co-author on the paper or anything. This was an attempt at not just recognizing objects and putting a box around them, but actually figuring out the outline of them. So this is called deep mask, and it's basically a convolutional net that's trained to kind of draw an outline of every object it sees. Not identifying the objects, just trying to figure out, where is an object, like, objectness, if you want. And that's the kind of mask it generates without telling you what the objects are. Then you can take those images and feed them to a recognizer to identify them. And the entire pipeline in the end is actually fairly complicated. So you get those object candidates through deep mask. It's sort of an improved version of deep mask. And then they go through various classifiers at various levels, and you train this for a few days on a big machine with 8 GPUs in it, and link 4 of them, and you train this with this elastic average SGD algorithm that was originally developed in my group at NYU and eventually was kind of re-implemented at Facebook. This Big Sur design, which you see a picture of here, is actually an open design from Facebook for a sort of machine learning supercomputer, if you want. So you can buy those things. I mean, the design is open. You can just buy those bugs from various vendors. Put a bunch of cards in them, stack them up. Put a bunch of several hundred or thousands or tens of thousands of them, like certain companies do, and then boil a small lake, training neural nets. So the results are really amazing. You get outlines with categories, cell phones, person, laptop. It detects people really well, even when it only sees a piece of them. Here's a kind of an interesting example here. I'm showing you the picture because you see those blurry people in the back. They are picked out as well, and that's kind of a mess.
That's amazing.
Yeah, actually, I totally hate broccoli, so now we can have a machine that actually picks out the broccoli out of your plate. So that's actually a mistake. So this shows you the limits of that system. It thinks that's a baseball glove. That's actually the head of the guy. So it figures out it's gonna have to do with sports, but the interesting thing is that this is taken from inside a car, and this is the dashboard, and it actually identifies this as a car, which obviously it is. Okay, a bunch of sheeps. Yeah, a bunch of sheeps. Now, unfortunately, it's not perfect in the sense that it cuts that sheep in half, but okay. Lamb chops. Donuts. There's no burritos in this one, actually. Giraffes, zebra. It doesn't actually work that well on zebra, so if you have, I don't think I have that slide, but if you have like multiple zebras, it gets like totally confused. It doesn't know where one zebra ends, where the other one begins, because, but then you think about it and you say, zebras actually evolved to confuse predators and actually, confuse vision systems to figure out, to know the boundaries between them.
This machine is actually a cheetah.
It's a cheetah, yeah.
What's the training set for the mask?
So this uses the so-called Microsoft COCO dataset. COCO stands for Common Object in Context. I think there is 200 categories, and if you 100,000 examples of various kinds. This COCO dataset is used for all kinds of stuff. It's also used for visual question answering, for captioning, for semantic segmentation, for all kinds of stuff. There's a competition that took place very recently. The results were actually published early December. There was a workshop at ICCV in Chile. So Facebook AI Research entered that system, and we placed second. And the question is, who was first? Microsoft Research Asia, and what they used was a pipeline that was very similar to ours, which is not surprising because one of the guys at Facebook who was working on this actually came from Microsoft. I stole him from Microsoft, and it's basically his pipeline, but except for the deep mask. So they didn't have a deep mask type idea, but what they had was a much deeper convolutional net than the one we had. So the convolutional net we use here is kind of a 20-layer convolutional net, which is fairly conventional nowadays. And they used a neural net with 152 layers. And that sounds insane when you think about it, but it actually brought about a pretty significant improvement. I think this pipeline with the very deep network actually would probably beat everything. Yeah, pretty good with food and stuff. Okay, so one of the big things that we do at Facebook also is face recognition. So when you upload a picture on Facebook, it's kind of tagged automatically if it's one of your friends. And there's a pretty big infrastructure behind that at Facebook. So Facebook gets, the Facebook website gets on the order of, the number changes every day, but it's on the order of 800 or 900 million photos per day. On average, there is more than 2 people per photo. And each of those photos goes through 2 pipelines. One does the object recognition, and the other one does face recognition. And the face recognition system has a face detector, which is sort of another kind of simple system that just picks out the face. And then the face is sort of normalized, size normalized. It's sort of unfolded a little bit, and so it's rotated so that it looks frontal. And then it's fed to one of those convolutional nets, sort of a particular kind. We call it deep face. And that one is trained, supervised to classify faces, but then at the end we have a way of applying this to recognize faces we've never seen before. So we can recognize, one person among, hundreds of thousands, if not millions, in a fraction of a second. And so this is clearly superhuman performance. It's not superhuman in the sense that it will need a fairly clear, fairly frontal view of a person to recognize that person, but it's able to pick out a person among a ridiculously large number that no human is capable of remembering. So that's really one of those cases where 5 years ago you would have told someone we have vision systems that have superhuman performance, and you'd have been laughed out of the room. And now we actually have a bunch that really work really well. We can identify the pose of people. We can generate captions for images. So the man you want, the one you want to look at is the one here, a man wearing skis on the snow, okay. A man riding a skateboard on a ramp, a woman is holding an umbrella, baseball player swinging a bat in a baseball field. So, we can generate things like this. It looks very impressive. It's not as impressive as it looks because this particular data set, again, is fairly restricted. So the number of different things you can say about those images is actually fairly small. And so it looks like if you were to show any image, it would do something sensible, but it doesn't. You know, there is sort of a relatively narrow domain of things that will work very well. Now, because of the success of all those recognition systems, a lot of hardware companies now are interested in basically producing specialized hardware to run convolutional net really efficiently on mobile devices and embedded devices. So I don't know how many of you here are fortunate enough to own a Tesla. Like, who needs a car in New York anyway? But the Teslas use a vision system built by an Israeli company called Mobileye, and that vision system uses a chip that runs convolutional nets to do basically, you know, navigation for the car. And so the car can drive itself, you know, keep in lane, detect obstacles in front, change lane, etc. And it's using a convolutional net for that. And there are sort of, you know, systems that Mobileye are working on that are very much inspired by the robot system I told you about earlier, running on their chip. NVIDIA is working on, you know, Qualcomm and Samsung. You know, all these guys are kind of working on convolutional net chips. So probably within a few years, you know, every one of these will have a conv net chip in them. And certainly your car will, if you decide to buy a car in New York, which, you know. So the other thing now, so we, you know, deep learning sort of created a revolution in speech recognition and image recognition. And it's about to create a revolution also in natural language processing. It hasn't quite completely taken over yet, in a sense that it is still kind of a battle of, you know, the people who are kind of, you know, doing deep learning all the way for natural language understanding and people who are sort of using a combination of different techniques. But there is one set of technique that is really, has become extremely popular, and it's not technically deep learning because there is no deep neural nets in it. But it's a form of unsupervised learning that has been inspired a little by deep learning. The first pioneering work in this area were done by Yoshua Bengio at University of Montreal, who used to work with me at Bell Labs, actually, and Ronan Colobert and Jason Weston, when they were working at NEC Labs in Princeton in the early 2000s. Both of them are now at Facebook AI Research here in New York. Actually, Ronan is in Menlo Park. And the more kind of recent and simpler incarnation of those ideas is something called Word2Vec. I'm sure a lot of you, who has heard of Word2Vec? All right, who has actually played with Word2Vec? Yeah, right, a lot of people, okay. So Word2Vec is this really cool thing which allows to learn a mapping from words to vectors in such a way that the vectors contain a lot of information about the word, the semantics, its syntactic role, and things like that. And it's a very simple idea. And by the way, Tomasz Mikolov also works at Facebook AI Research in New York. I hired all these guys because, you know, it's really cool work. So basic idea is very simple, and there's several forms of it, but the basic form, at least a simple one, is you take several words in a text, a window of words in the text, and you train some neural net of some kind to predict the word in the middle. Okay, you don't show it the word in the middle, you just train the network to predict the word in the middle. And if this neural net is to do a good job at predicting the word in the middle, it needs to basically figure out how to represent those words by a vector. You know, the first layer here is basically a lookup table that turns each word in the language into a vector. Okay, a lookup table of vector. It's a big array, and it's trained. You know, this is all neural net trained with backprop, and it trains to predict the word in the middle. And if it does a good job at this, it has to extract something about the meaning of the words and, you know, what other words can appear in conjunction with those words. There's lots of simple methods to do this that are based on SVD and PCA and stuff like that, but Word2Vec is sort of a nonlinear version of this, if you want. And this is very popular for a lot of applications in natural language understanding. So one particular property that emerges naturally, and there is some theory that explains why, but it was a bit of a surprise when people first figured it out, is that if you take the vector for Japan and the vector for Tokyo, and you subtract Japan from Tokyo, you know, you get this vector, right? And you subtract, Berlin from Germany, Germany from Berlin, you get that vector. And it's basically the same vector. So you have something like, Tokyo minus Japan equals Berlin minus Germany. A relationship is basically a vector of particular orientation and length, which means you can do algebra instead of logic. So you can say, Tokyo is to Japan as Berlin is to Germany, and if I take Tokyo minus Japan plus Germany, I get Berlin. So you can do algebra instead of reasoning. You can replace reasoning by algebra. And that's really cool, because normal reasoning in the old days, in the good old-fashioned AI, reasoning had to be done with logic. And it's very difficult to combine logical inference with machine learning. You can't train a system to figure out how to do logic, basically, because it's kind of a discrete thing. Whereas now, if you replace logic by algebra and linear algebra in particular, but operations on vectors, now you can propagate gradient through that. So you can train a machine to do the proper inference, and etc. There's a lot of excitement about this kind of approach. So one example of this is question answering. So this looks like a complicated thing, but basically, imagine you have a knowledge base, and the knowledge base is represented by a graph, basically entities and relationships. So, for example, George Clooney is an actor, and he's male, and he's born in Lexington, and he played in Ocean 11, things like that. Okay, so each of those things is a different relationship. What you can do is you can take pairs of entities and their relationship as kind of very sparse vectors, and using something a bit like Word2Vec, or using a lookup table, map them to a vector. Okay, so a vector will represent entities and relationships. And then similarly, you can take questions in text, and then also run them through an embedding kind of lookup table type algorithm. And we're going to learn those lookup tables in such a way that whenever a particular object or relationship here is the answer to a particular question, the vectors will be nearby. And whenever a fact is not the answer to a question, their vectors will be far away. And you can run learning algorithms. So there is contrastive learning algorithms that are designed to do this. In fact, some of them were invented by Jason Weston, and there's a particular algorithm called Wasabi to do that. It's an acronym. I can't remember exactly what it means. This was work done by Antoine Borde, also at Facebook here, and Sumit Chopra and Jason Weston. And so you can train those things to answer questions, and so there's some degree of generalization. Another thing that has people excited is the use of so-called recurrent networks. And so these are neural nets that kind of have loops, if you want, and you can sort of unfold those loops to turn them into feed-forward nets. And people have used this to do translation. So probably one of the hardest topics now is how to do translation of language using neural nets, particularly recurrent neural nets. And the latest competition that took place just a few months ago was won by a system from Stanford, which actually uses this kind of system for translation. It's very impressive because the margin by which they won was actually also pretty good. So you're starting to see the same kind of phenomenon in natural language understanding machine translation that you saw in speech recognition and image recognition. Yeah, I'm not going to go into the details of this, but it's really cool because you can train those systems end to end, and there is no knowledge of linguistics or anything like that. It's just giant neural nets and lots of GPUs. So this all contributes to the idea that we should represent thoughts or concepts by vectors. At Facebook, we have a project that we call Embed the World, which basically the idea is to map every entity on Facebook into a vector so we can compare things. So we have a vector for a piece of content and a vector for a user. If they kind of match in a particular way, we can say that this content is likely to interest that user. So of course that would be good for feed ranking and things of that type. Content filtering, search, all kinds of stuff. Okay, but there is a problem with recurrent nets, which is that they don't remember anything. So if you use a recurrent net to read a story, and then you train it to basically tell you what was the story about, like do a summarization of that story. By the time the neural net has read the story, it's forgotten the beginning. And there is sort of very deep theoretical reasons for why it's very difficult for a recurrent neural net to actually remember things. So one of I think the big breakthrough of the last year or two is the idea of augmenting recurrent neural nets with memory. but it has to be a memory through which you can propagate gradients. It has to be kind of a soft memory, if you want. And there were ideas along these lines in the late 90s. A type of recurrent net that is very popular is called LSTM. That means long short-term memory, and that was proposed by Reiter and Schmidhuber back in 1997. It was the idea of also having a little piece of memory attached to a recurrent neural net, but it was sort of like a register. What we're talking about here is like a big memory, if you want. So how do you make a RAM circuit soft so you can propagate gradient through it? DeepMind has also been working on similar ideas where by a model they called neural Turing machine. It's kind of an interesting story about this actually. Jason Weston at Facebook and Sumit Chopra and Antoine Borde started working with memory networks and published a paper on the archive.org. And the DeepMind people had been kind of working on the neural Turing machine for a while. And they tend to not publish things until it's really ready, because they can make a big splash and send it to a journal. So they don't put stuff on archive. But as soon as they saw this paper, within days they put a paper on their neural Turing machine because they were afraid that we're going to steal their their thunder or something. So there's a bit of a interesting competition between Facebook AI Research and DeepMind on this kind of topic. But we also cooperate because we both use the same machine learning software platform. We both use Torch. Any of you here heard of Torch? Okay. Yeah, maybe people have taken my class at NYU. So, yeah, Torch is sort of a development environment mostly for deep learning, but for anything numerical, essentially. So it's basically a numerical library, sort of tensor manipulation library, and on top of it, sort of a deep learning kind of environment, and it uses Lua as the front-end language. Lua is very simple, very fast, and it's not as popular as Python. Doesn't have all the ecosystem of Python, but it's got a bunch of advantages. And so both DeepMind and Facebook AI Research and Twitter use Torch as the main development environment. Now Google has put out TensorFlow, which is sort of a kind of a competitor, if you want. And TensorFlow, to some extent, plays a different role. It's better for deploying deep learning systems, but not so much for research and experimentation, because it's much more difficult to define your own module than it is in Torch. So they kind of occupy slightly different spaces. And the latest work on this is what's called the end-to-end memory network, and also there is another work at Facebook called Stack Augmented Recurrent Nets by Armand Joulin and Thomas Mikolov, which is sort of a stack machines. Recurrent net with kind of a stack, if you want. And those things do amazing things. So they can do things like, you give them a 15-sentence version of Lord of the Rings, right? I mean, don't read the last 3 sentences if you haven't seen the movie, because it's kind of a spoiler, but or the last 4 actually. Sauron died. But that's pretty much all that happens in Lord of the Rings. And then at the end, you can ask questions. Where's the ring? And the machine says Mount Doom, and where's Bilbo now? Grey Heavens, blah, 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 blah. And that's because it can remember what, in this memory, what happened, and then it learns to pick out the right relevant fact to answer a particular question. So that's the... Okay, so I'll end by talking about obstacles to progress towards AI. So I constantly get the question when I talk to the media of when will we have human level intelligence, and when will Terminator kill us all and all that stuff, right? So and what I have to say is that we're still very far from it, because not just because of the power of the computer that's limited, but also because there are basic concepts that we just haven't grasped. And the main thing is the main concept we haven't grasped is unsupervised learning. But before that, there are things that we're working on. So things like integrating representation learning or deep learning with reasoning, attention, planning, and memory. So this is things that are very active topics of research. People are doing things like, teaching neural nets to play Go or play StarCraft or play Atari games and stuff like that. And it's basically this, the idea of sort of combining reasoning, planning, etc., with and actions with deep learning. Integrating various types of learning as kind of one single algorithm, if you want. So supervised, unsupervised, reinforcement learning. Those are 3 types of learning that currently use different algorithms. It'd be nice to use one. And effective ways to do unsupervised learning. In my opinion, that's the biggest obstacle to making progress, significant progress in AI. And so reinforcement learning is the type of learning where you do something and then after a while someone tells you if you did well or not, or basically you fall off your bike and you realize you made a mistake, but you don't know which mistake you made. Supervised learning, we all know, instead of being given a scalar value once in a while, which is what reinforcement learning gives you, you're given a label, so it's more information for every sample. And then supervised learning, you're not given anything. But the question is, what principle do you use for unsupervised learning? And one that is somewhat gaining in popularity is the idea of prediction. It's an old idea. It goes back 30, 40 years. But it's the idea that you learn how the world works by just observing, and you learn to predict what's going to happen. So the way we learn as animals and humans is by observing the world and training ourselves to predict what's going to happen next. So the better we are at predicting the future, the smarter we are, and that's what unsupervised learning is about. And so in a way, the joke I say, and this is basically to upset my friends at DeepMind, because they're really hung up on reinforcement learning. So what I say is, if machine learning is a cake, the unsupervised learning is the cake itself. Supervised learning is the icing on the cake, and reinforcement learning is the cherry on the cake. And the problem with this is that we know how to do the top two. We have no idea how to do this one properly. And so we're kind of like the physicist, right? Unsupervised learning is like the dark matter of AI. It's always 95% of the mass in the universe, and we have no idea what the hell it is, or how to approach it. So, that's the that's the problem we're facing. How do we do unsupervised learning? And we're working on things like trying to predict videos. These are a few examples. In each of those little animations, the first 4 frames are real frames, and the next 2, which are signaled by this red border, are predicted. And that system is doing a pretty good job at predicting what the future. Only 2 frames in the future, but we have to start somewhere. It's much better than sort of classical methods, which are basically this, that predict completely blurry stuff. And I'm going to end here, and thank you very much for your attention. Okay, I took a lot more time than I thought.
So we have a tradition in my meetup. After every talk, we're gonna vote how well the talk is. I'm gonna ask Professor LeCun to turn his back to you, so you can tell me your honest opinion. Professor LeCun, would you mind standing here? So.
I was hiding.
No, you were gonna see it. So if you don't like his talk, you can do this. If you think he's good, you can do this. If you think he's awesome, you can put your thumb in the ear. So I will give you 5 seconds to think. 5, 4, 3, 2, 1. Tell me how you think of him. Okay. So based on my face recognition, 90% of people put your thumb in the ear. Okay, next we're gonna take exactly 16 questions. And for the good one, we're gonna give you a t-shirt. And you can tell me whether they're asking good ones.
Ha.
So you said your system,
You said for deep nets, you don't have to featureize by hand. You don't have to wonder about some interesting features. Do you ever look retrospectively at what features the deep net discovered? And can you make you might be able to look at them and see that there's some sorts of filters, but can you ever make semantic sense of what they are?
Mostly not. So, some people have been doing this. So in particular, Matt Zieler and Rob Fergus had a paper a couple of years ago, 3 years ago or so, where they actually tried to analyze what the features were that were extracted by a convolutional net trained on ImageNet, and trying to make a pictorial representation of what kind of input pattern will maximally activate a particular detector. And what you could see was, I had this slide at some point in one of my talks, but what you can see is that the low-level patterns that are detected are essentially oriented edges, and then you start, at 2 or 3 layers up, you start seeing things like wheels and honeycomb and sort of basic patterns, repeated patterns, and then a couple layers up, you see parts of objects, things like that. So the interesting aspect of this is that you have this idea of hierarchy where as you progress in the layers, the features that are detected, the kind of patterns that are detected are kind of more global, more abstract, have more variability to them, and cover a bigger part of the image. And that's exactly what these things are designed for. But usually we don't try to analyze too much, to overanalyze.
Well, I'd be interested in like identifying features that are surprising, ones that you wouldn't expect to see.
Yeah, well, yeah. I mean, a lot of people ask this question because very often. I mean, I'm sure a lot of you are familiar with this, where you work with a customer or user of the system you're building, where they ask, why is the system making that decision? And if you have a logistic regression model, you say, well, that weight is much bigger than all the other weights, and that feature is on, so that's probably why. You can do sensitivity analysis very easily. Just the weights. And in fact, there's been an argument against neural nets for very long that they are black boxes. It's very difficult to kind of figure out why a neural net is making a particular decision. It's not that difficult. You can also come up with explanations by doing sensitivity analysis. You can compute the gradient of every output with respect to every input and say, if I change this part of the input, the output is going to change, so that part is critical. People have done this. In fact, they've used this as a way of localizing objects and figuring out what's important in the image to make a decision. So you can always do that. It's just that it's not as useful as people think it is. When a lot of what you do is building predictive models, and explanations are not that useful. In fact, they're reassuring, but they're not very useful.
Down here.
Hey.
Thank you for a great talk. It's always super interesting to hear you talk about this stuff. I'm really interested in inferring human context from spatial temporal time series data. So, like inferring somebody's place of living and their work and their gym from accelerometer data and GPS data. And then you can think of something that's a simple thing you could probably do with an expert system fairly easily, but then something more abstract like human emotion from those same signals. Is that something where deep learning could already be applied? Is that just a reapplication of technology we already have? I know it's kind of a similar problem to streaming video, or do we need new technology to be able to do something like that? And if so, where would the research be?
Yeah, so we can do video action recognition pretty easily. Speech recognition you could think of as kind of a sequential model, so is text. So for time series like accelerometer, for example, outputs, some of the best methods are either what's called time delay neural nets, which are basically temporal convolutional nets, or recurrent nets, where and people use this in finance, for example, for stock market prediction, whatever. People have used this for in bioinformatics to figure out the interactions between genes, like gene regulation networks, things like that. So you get a multidimensional temporal sequence, and either try to classify a segment of it or predict the future. We've done this actually several years ago also from EEG data, so electroencephalogram data for predicting epilepsy seizures. So the idea would be to build a little implantable widget inside the skull of epilepsy patients. And when the system predicts that the patient is going to have a seizure, you sort of inject a little bit of drug to kind of prevent it from happening just at the right location.
Is that published?
Yeah, it's published. Yeah, it's in where is it? I can't remember which journal it's in, but yeah, the first author is Piotr Mirowski, Mirowski. He's a former student of mine, also at DeepMind, and you'll find it on my webpage.
Thanks.
How do you decide on the network topology, the number of layers, layer sizes, and so on? Is it the more the merrier, or is there some?
Yeah. So how do we construct those architectures? So the thing is, like once you've decided on using convolutional nets, for example, the number of parameters you can play with is relatively limited, and there is only a a relatively small number of combinations that make sense. And people have come up with sort of different concepts of how you build those things. So the latest idea about convolutional nets, you should use many layers and very, very small convolution kernels. So we used to use something like 5 or 6 layers with kernels of size 7 by 7 or something like this. And the best models now have something like 20 or 30 layers with 3 by 3 kernels. And the pooling and sort of dimensionality, spatial dimension reduction is something also where people have made progress recently. So, once you've kind of decided on a set of parameters like this, you just fire up your room full of GPUs and try different things and see what sticks. But to first order, the larger you make the networks, the better they work. Yeah, which is very surprising. It's contrary to what every textbook in statistics will tell you, because if you have too many parameters, you overfit. But it's not true with those neural nets.
As someone who's is very interested in AI, I know that reinforcement learning is a very sort of fundamental part of AI. And do you have any sort of explanation why the focus on deep learning has been more on supervised and unsupervised learning rather than reinforcement learning, which I think really only DeepMind's Q-learning or DeepQNet in 2014 was sort of kind of a breakthrough. Why is it only recently been explored?
Yeah, so DeepMind is really hung up on reinforcement learning for various reasons. It's partly because of the history of it, and because it's very linked with the Gatsby neuroscience unit, where the researchers there were very interested in sort of mechanism of reward in the brain. And Demis Hassabis himself, the co-founder, has worked on reinforcement learning. And some of the other co-founders also are very much in that stuff. So that was sort of a kind of working hypothesis for them. And the work they did on learning Atari games using convolutional net and reinforcement learning, the second author of that paper is a former student of mine, Koray Kavucholu, so is the convolutional net guy, and then the other people are kind of the more reinforcement learning people. It's really cool work. It's only practical for things like games because, as I said earlier, the information you give to the machine or you ask it to predict really at every step of a reinforcement learning, when it plays Atari game, whenever it doesn't die or whenever it marks a point, it gets a reward, and that's just one little value once in a while. And so, if you want to train a network with millions or hundreds of millions of parameters to learn anything in these kind of conditions, you'll have to have millions and millions and millions of trials. And so it's nice if you have a really fast Atari emulator because you can run this in parallel on multiple machines and it will train relatively fast. But in real situations, like in the real world, if you have a real robot, you basically can't use reinforcement learning. The system already has to have learned most of the basic concepts before you use that. That's the argument I have why the reinforcement learning is the cherry on the cake. So I don't think it's practical to rely on reinforcement learning that much. And even supervised learning has that limitation. You have to have armies of people who kind of label images all day if you want that stuff to work. So that's why I think the future is in unsupervised learning. We just don't know how the hell to do it.
In your world to vector sort of approach, how do you choose the vector space? So not every vector space, for example, would give the mapping that you found with countries and capitals.
Well, so it's a Euclidean vector space. Okay, it's vectors of a particular dimension. You choose the dimension a priori, and you can try several and see what works best. Typically, it's a few hundred, the embedding dimension, and you compute Euclidean distance or dot products in that space. So it's a Euclidean space. And then you train those vectors, you train the lookup table that maps words to vectors in such a way that vectors that represent similar contexts, concepts are nearby. And that's just a side effect of training the system to predict what word occurs in the middle. Or, in fact, there are several forms of word to vec, but that's one of the most popular ones.
Briefly talked about how one of the challenges is stitching together various algorithms. Can you talk about in more detail about those challenges and how different scientists have tried to address them?
So you're talking about which challenge?
So you were talking about among the challenges are you have algorithms, say one in image recognition and another in NLP.
Right.
So stitching together multiple types of algorithms
Yeah.
into one kind of broader intelligence.
So there is an interesting phenomenon first, which is that it used to be that speech recognition, natural language understanding, image recognition, and even video processing were completely different fields with different people, basically not talking to each other. And what we've seen over the last few years is that all of those things now use the same basic methods. So, image recognition uses convolutional nets, video recognition uses convolutional nets, speech recognition uses convolutional nets, with other things on top. For language processing and language modeling, it's basically recurrent nets, mostly LSTM type recurrent nets. For things that have kind of reasoning and memory, you have memory networks and memory augmented networks of various kinds. And so now it's coming to the point where when you need to build like a system, for example, that turns images into sentences that describe them, you take a convolutional net that you train on ImageNet or whatever data set, and then you stick a recurrent net on top of it that's trained to generate text, and then you kind of train the two together so that they generate the right text. And so, and all of those software platforms that people use for deep learning are designed so that you can assemble blocks, functional blocks, things like convolutional net, it's a block and it's composed of, layers of various types, convolutions and pooling and ReLUs and blah, blah, blah. And all of the, complications of how you compute gradients, basically you get for free out of those infrastructures. By assembling the blocks, each block knows how to compute its output as a function of its inputs, but it also knows how to propagate gradient through itself. And so you get a learning machine by default, essentially, by assembling those things. So I think what we're going to see in the future are very complex pipelines that are combinations of those modules, all sort of differentiable, all trainable, and all globally trained.
So I guess it sort of falls on a little bit. If you have success with one model, let's say it's a supervised model or maybe it's an expert system or something, can you use that to jumpstart a supervised learning system so that it would begin having some success quicker, or do you have to start from white noise and hope it gets it?
Well, so one thing you can do is you can train you initialize your network with generally just random initialization. But what you can do is pre-train your network with data that you generated by a system you already have, for example, right? So if your system has some level of reliability, you can use it to generate data with which to train your neural net first, and then add real data to kind of fine-tune for the task. But there is no smart way of initializing neural nets.
I have a question a little bit on a higher level. So I know there's been a bunch of starts and stops in the progression and evolution of deep learning and AI. What do you think has kind of propelled the recent dive into it, either from a hardware standpoint and where do you think that next step will be? What do you think we need to do in order to get to that next level?
Right, so to get to the next level, I basically made the point, it's solving the unsupervised learning problem, figuring out how to do unsupervised learning. I can get into the kind of technical issues that are posed there. I mean, the main issue is that if you want to base unsupervised learning on the idea of prediction, like so, I give you a few frames of a video and I ask you predict what's going to happen next. There is a lot of, the world is intrinsically unpredictable in the sense that there's a lot of things that can happen. And if you train a neural net of some kind to predict what effectively happened, there's probably another video where something slightly different happened for more or less the same context. And so the best thing the system can do is predict some sort of average of all the things that could possibly happen, which is why you get those blurry predictions. The animation on the top here, that's basically what it does. And so the question is, how do you get a machine not to predict a single prediction, but to predict a number of different possible futures, if you want, without penalizing it for picking one in particular? So word2vec has that problem because you can never predict exactly what word is in the middle of a sentence or what word is going to come next. But in the case of word2vec, we actually have a simple way of representing a distribution over words. We just give a big list of numbers that are positive and sum to 1. The system just produces distribution over words. So it knows it's possible to handle uncertainty in the case of discrete objects. But for video, we have no idea how to do that. How do we represent a distribution over all possible frames that can happen? We don't know how to do this efficiently. So that's part of what we do here of basically training the system to, not be punished for not predicting exactly what's going to happen, but for predicting something that seems reasonable, even if it's not exact.
You need a quantum field theory of unsupervised learning.
Quantum field theory of unsupervised. Yeah, you need a certainty, or just probability. You don't.
Well, I mean, like, you want a distribution over fields, where every image, every set of pixels is a field.
Well, it's arguable whether you even want a distribution. You don't necessarily need to give a probability for everything that can happen in the future. What you want is tell whether it's possible or not. Whether it has any likelihood of happening or not. So I think there was.
So what work do you know about?
Excuse me, can you put it a bit closer? I have a hard time.
Yes, it's an application question, and I'm interested in hearing about what work is being done to detect certain types of content like terrorism. That's a big issue now. Like label videos, photos, chats, and how effective do you think this will be to label?
So I missed the key word. What detection?
How effective will this deep learning be?
For what kind? Detecting what?
Terrorist content.
Oh, terrorist detection. I see. Okay.
Knowing what's being done about it, to have some tools to identify that.
Well, there's a lot of three-letter word agencies that are very interested in this. But, obviously that's what they do for a living. So, they're interested in things like, keyword spotting or from audio, from, phone conversations and stuff like that. They're interested in, and I don't work for them. I don't talk to them. So I'm kind of, this is from what I hear indirectly. Well, so yeah, when you companies like Google and Facebook have to deal with this. So we have to deal with one of the things that we have to deal with is, for example, people posting very very offensive content, like some ISIS group posting a video of someone heads being cut off. So you kind of have to filter this before it gets to the user because it's really upsetting. And so we do use image recognition, video recognition to filter out content, pornographic content, stuff like that. Things that doesn't fit into the terms of use of Facebook, whatever. So there's some of that going on. It's very difficult though to when it starts to get into like political questions. Like for example, in the U.S. You can say all kinds of things. You can deny the existence of the Holocaust, but you can't do this in Germany. It's illegal. So it's very difficult to sort of take a. You start to get into a territory where you sort of build. It's based on opinions. Basically, it's very difficult. But the technology is certainly possible. So yeah, I don't know how the microphone works. So.
Okay, one more question. Can you take two or?
I'm fine with two. Yeah, sure. It's whoever. You guys can leave whenever you want.
So I'm curious if. Oh, sorry.
I think it's not on.
It's off.
Can I see it?
Just shout it.
Okay. Yeah, I can be as loud as I can. So during this process of learning, is the machine aware that is it aware that it is learning? And are we able to make the machine aware that it's learning through our future explorations in unsupervised learning?
No, it's not aware of anything. This is going to take a while before machines are aware of anything. To some, I don't know. Sometimes when you train a robot to do a task, it looks kind of eerily natural, like animals. But certainly there's really interesting work now going on in Peter Abel's group at Berkeley, where they use deep learning for basically teaching motor skills to robots, robot arm, like for grasping and things like this. And it's really cool. It's really cool stuff. This is the same Peter Abel that a few years ago used reinforcement learning to train a system to fly like aerobatic helicopter. It was pretty cool stuff too. And no, no, the machine is not aware of anything. Come back in 20 or 30 years.
Do you think that, like on our term path, we'll be able to do something?
Well, I mean, it requires breakthrough that we don't know if we can make. I mean, there's people who just say, it's just a matter of computers becoming more powerful, and eventually we'll just figure out the ideas for how to exploit it so that we make intelligent machines. If you read all the futurists, they say we'll have computers as powerful as the human brain, around 2040 or so, and so by then we'll have machines that are as intelligent as humans. I mean, to some extent, we already have machines that are more intelligent than humans. You can buy a little gadget for $30 downstairs at Kmart that will beat you at chess, right? Soon it will beat you at Go, and so to some extent we already have that. But they're very specialized machines. They're very narrow intelligence. So the question is, how do we get machines to be sort of generally intelligent, based on the idea that somehow humans are generally intelligent? We're not. We're very specialized as well. There's a lot of things that we can't do very well, and so there's a lot of basic problems we have to solve, like how do we do unsupervised learning, and how do we scale this up, and how do we merge supervised and unsupervised reinforcement learning in one scheme? How do we make sure all this is stable? How do we build basic drives? Humans operate in a particular way. The reason we do bad things to each other, for example, is that we're built to kind of we have self-preservation instinct. We have to feed ourselves and things like that. So we have basic drives that make us do things in a particular way. There's no reason that machines, intelligent machines, will have the same drives unless we build that into them. But I don't see why we would. So, there's a lot of major questions we haven't answered. We're nowhere near building general intelligence.
Early expert systems that did diagnostics and had a problem of being brittle, such as deciding that a man could be pregnant, was one of the problems. Right. To even current systems that you do with deep learning, you have this problem of brittleness. Do you really believe that with unsupervised learning you can solve the brittleness problem?
Yeah. So, I mean, the diagnostic system that predicts that a man is pregnant basically doesn't have common sense, and it's basically because the person building the expert system didn't put the fact that men cannot become pregnant. So there is a company that's been around for 25 some odd years in Texas called Sycor. It's called Lucid now. Actually, it's been bought, I think, and they have a whole bunch of people just writing facts all day, and they have an inference engine, and Doug Lennart, used to be kind of a major guy in AI, is sort of the only one now really pushing for good old-fashioned AI of this type, where you just collect, millions and millions of facts and have just a logic inference engine that deducts every possible facts. But you have to enter every possible facts, things, completely ridiculous things that we all take for granted because we know how the world works. And so I think it's completely hopeless, frankly. Some of the people who work in this company I've known for a long time, and I feel sorry for them, some of them, because they want to incorporate some machine learning in this, but it's sort of a little complicated. So I think the way to go there is really unsupervised predictive learning. We just have to figure out how to do that properly.
But as humans, what we do is in the stage that we're toddlers in the learning, the representation that we have of knowledge, we totally lose by the time we're like 5 or 6 years old, and we change our whole representation. Can we do that with unsupervised machine learning?
Yeah, I think so. I mean, there are things. It's surprising how much we learn when we're babies. So when we're babies, we don't know that the world is three-dimensional. We learn that. We don't learn that there are objects that can move independently of others. We learn that as well. We don't know that. In fact, that's very well studied. Babies don't have the notion of object permanence. So if you hide an object behind another, it's as if this object doesn't exist anymore to them, which is why peekaboo is so much fun, right? Because you're not here, and now you're here. So, it takes a few months before babies kind of learn that, objects are still there after you occlude them. They learn this in a few months before they can talk, and we can, psychologists have ways of figuring out how surprised babies are by things that happen, and so they can sort of, probe really what kind of physical concepts they've learned. So all of those things we learn, and these are things that we learn by observation, by interacting with the world, by acting on it, and that's the kind of learning that we need to reproduce in machines that we really haven't done at all. And again, that's the dark matter. That's 95% of the mass of the universe, if you want.
But I'm also asking about the representation, how we represent it.
Well, so yeah, I mean, that's the whole premise of deep learning is learning representations of the world. And so the question is, if you want to, so for example, if I want to predict what the scene is going to look like if I move 1 meter to the left, I have to have inferred that the world is three-dimensional, and that and that you are in front of the camera, for example, because I cannot predict how you're going to move relative to the camera unless I have figured this out. And so, to do a good job at predicting, you have to build good representations of the world. That's kind of a side effect you get kind of naturally out of it. That's why we're so interested in predictive unsupervised learning.
Hey, so I have two questions for you. I watched a TV episode called Black Mirror, produced by BBC. And one of the episodes is about one woman lost her husband, and he ordered a virtual one online. And the AI company was able to replicate how her husband thought in response to questions and make him like a real person. So how close we are to replicate a person?
We're probably pretty close to like parlor tricks that will fool people for a short time, but not really to the real thing, in the sense that so right now you can take this thing that Andrei Karpathy had, who is PhD student at Stanford, who built using Torch. It's a recurrent net training script, basically. And you can train it on any text. You can take a piece of text or anything and train this recurrent net as a predictor. So it's going to predict what word comes next. And people have trained this, I've picked up his code and trained it on, Obama speeches. And you can run this thing and it's going to generate Obama speeches, in the style of Obama. They're not going to say anything useful, but they're going to talk about they're going to have all the buzzwords, and the style is going to be right, and it's going to have the right emotional things and all that stuff, but it's going to be meaningless. I think it'd be easier with Sarah Palin or something, but Trump.
Last question: how can we build a small deep learning machine for ourselves, or try it, get our hands dirty?
Oh, that's super easy. So you either get time on AWS, or buy yourself a nice gaming rig, a computer with a decent CPU and a high-powered GPU card, and a high-end gaming card, basically, and install Linux. Wipe out Windows. You don't need it. Install Linux, and install CUDA from NVIDIA. Install cuDNN, which is the NVIDIA library for deep neural nets, and then install either Torch or Theano or Keras or TensorFlow, depending on your taste. And then there is a whole bunch of things you can download. You can train your own convolutional net on ImageNet, or you can play with recurrent nets, and you can experiment with this. I think Torch is more flexible. I think it's easy to learn if you start from scratch, but it's Lua, it's not Python. So if you're familiar with Python, I would probably recommend Keras. So Keras is sort of an API on top of, which basically is very similar to Torch in spirit. So it's got the same idea of blocks that you assemble. But underneath, you can use it to either generate code for Theano, which is sort of a built-in thing that was developed by Yoshua Bengio's lab, or for TensorFlow, which is the Google thing. TensorFlow is kind of slow at the moment. The version that Google released is not great, for performance. But so if you want fast, you're better off with Torch. If the only thing you're interested in is convolutional net for computer vision, then you don't even have to deal with any of this. You can download Café. So Café is sort of a C++ library with sort of a thin Python layer on top, and it's really designed for convolutional nets. It's not very flexible. It's not good for like any research or recurrent net and stuff like that. But if you just want to train an image recognizer, that's probably the simplest way.